Good afternoon, dear students. I am Dr. Sudarshan Behra, working as an assistant professor in SR University, Warangal, in the Department of Computer Science and Engineering. In the last class, we discussed what is context-free grammar, what are the components of context-free grammar, and what is a derivation, what are the different types of derivation like leftmost derivation and rightmost derivation, and how the parse tree or the derivation tree gets generated through the derivation process, and how the syntactic validation of a string gets checked by the syntax analyzer. In addition to that, we also discuss what is an ambiguous grammar and how ambiguous grammar creates difficulty for the syntax analyzer. Today, we'll discuss another kind of grammar as a part of the continuation of the last lecture. We'll discuss what is left recursive grammar, and we'll see whether that grammar is helps the syntax analyzer or it creates a barrier to the syntax analyzer. Okay. So as we discussed in the last class, you see here the parse tree. It's ambiguous grammar. So this ambiguous grammar, remember, this ambiguous grammar is a context-free grammar which generate multiple parse tree, like it has more than one leftmost derivation or more than one rightmost derivation for a single tree. So if that is the case, it generates confusion. It generates confusion within the compiler. So that means it creates ambiguity within the syntax analysis. So that is why this particular grammar is not accepted by any one of the syntax analyzer or the parser. You can say parser is of two types, as we just discussed last time. One is top-down parser, another one is bottom-up parser. So neither of the parser accept this ambiguous grammar. Okay, because it creates confusion, it creates ambiguity within the parser. So ambiguous grammar creates confusion because it generates multiple parse tree for a single string. Different meanings can be generated. Compiler may not know which interpretation is correct. Syntax analysis becomes difficult. Okay, so these are the problems that has been seen because of the presence of ambiguous grammar. So none of the syntax analyzer or parser accept ambiguous grammar. Okay. Now the question is how to remove ambiguity. Yes, this can be removed. The grammar can be modified. This can be removed by two methods. One is operator precedence rule. Another one is associativity. Okay. This is now not that much of important to discuss in this class. Okay, because we are just discussing, we are understanding how to generate sentence by using context-free grammar. So this discussion we can make some other time. Okay, how to remove ambiguity. Next, we'll discuss another type of grammar called as left recursive grammar. Try to understand or try to read the definition. A grammar is said to be left recursive if a non-terminal symbol appears as the leftmost symbol on the right-hand side of its own production. That means if a non-terminal producing something and if the same non-terminal is appearing as the leftmost non-terminal of the right-hand side of its production, such kind of grammar is called as left recursive grammar. For example, the form is given A derive A alpha. See, A is left-hand side non-terminal is deriving something. What it is deriving? It is deriving A alpha. Okay, alpha can be anything. Alpha can be epsilon. Alpha can be any combination of terminal or non-terminal. and alpha can be another A, alpha can be terminal. Okay, that is secondary. But you see, the same A is again deriving A first. In the right hand side also A alpha, okay, the capital A is the leftmost variable in the right hand side of the production. And which is, I mean, here you can say A is generating itself first, then it is generating alpha, no problem. But A is producing itself first. This kind of grammar, okay, when the leftmost variable of the right hand side of the production is equal to or identical to the non-terminal present in the left hand side of the production, such type of production is called as left recursive production. And the grammar is ultimately known as left recursive grammar. Okay. So where A is a non-terminal, in this form, A derive A alpha, A is a non-terminal, alpha is a sequence of terminal or non-terminal. Okay. Since A appears again at the leftmost position, the grammar becomes left recursive. So if A derive A K, then that grammar is left recursive. K may be anything, K may be a terminal, K may be a non-terminal. But here A is identical to A. Okay, I mean the left hand side of the production is equal to the leftmost variable of the right hand side of the production. Very simple to remember or understand. Okay, if I am writing B equals to BZ, it is not, much focus need not to kept on Z. You just see B deriving BZ. I mean B deriving B. So B is equals to B. There the production is left recursive, which makes the grammar left recursive. Okay. So such kind of grammar is also not accepted by any one of the parser, top-down parser or bottom. Okay, because this type of grammar, it has been seen that this type of grammar leads the parser into indefinite loop. I mean, it is a kind of a recursion. Okay, A derive A alpha. If you again replace A by A, then the same thing may occur. A derive A alpha, A derive A alpha. Again and again, same thing will be repeated. So it makes the parser to reach to a particular uncertain loop, indefinite loop. So that is why this grammar is also not accepted by neither by left, your top-down parser, nor by your bottom-up parser. So this left recursion has to be removed. It is easily possible. Every grammar, every left recursive grammar can be converted to non-left recursive. Okay, let us see an example of left recursion. Here another example you see, E derive E plus T. That means first E is in the left hand side of the E present in the left hand side is equal to the E appear first in the right hand side. So that is recursive. Then E derive T. This production does not have any recursiveness. Okay, because E is a separate variable on non-terminal and it is producing T. T is a separate non-terminal. So there will be no connection between, no recursiveness. Okay, no self-calling. Okay. So here the production, only one production is left recursive. What is that? That is E derive E plus T. Is left recursive because E appears again at the leftmost symbol of the right hand side of the production. Okay. But the second one is not non-left recursive. That is okay. But anyhow, either if if there are two productions, three productions, five productions, 10 productions of a grammar, if a single production contain left recursive, the entire grammar becomes left recursive. That is the thing. Okay, the entire grammar can be called as left recursive. So that is why it is essential to remove left recursion from the grammar. Okay. See here one example is given. Another example. Okay. Another example: A derive A alpha, and capital A derive capital A alpha, then capital A derive B. There are two productions. Okay, A has two productions. One is A alpha, another one is B. Then which one of the production is left recursive? The first one, because A derive A. A derive A alpha. Okay, so first one is left recursive. Okay. Why left recursion is a problem? Left recursion creates problem in top-down parsers such as left recursive descent parser or LL1 parser. Okay. So it may leads to indefinite. It may leads to indefinite. I don't know infinite loop. I mean infinite recursion. So that is why this particular grammar is called as is a problem. Left recursion is a problem. The non-terminal A call itself immediately from the left side. Okay. So in this particular grammar, okay, only one left recursive production is available. That is A derive AR. We'll take another example here. The previous example given E derive E plus T. The parser tries E derive E plus T. Again, see why what kind of problems actually appeared. That problem is stated here. Okay, let us say there is a production E derive E plus T. The parser tries to find out E derive E plus T. Again, E derive E plus T. Again, E can be replaced with E derive E plus T like this. It will continue for infinite time. Okay, it may continue. So in that case, it leads the parser to enter into an infinite loop. Okay, so that is why this particular left recursiveness or the left recursion grammar need to be avoided. Elimination of left recursion. How to eliminate left recursion? There is a formula. Okay, the left recursive grammar can be converted into non-left recursive grammar. The original grammar is A derive A alpha or beta. Let us say A derive A alpha or A derive beta. You can write in one line also by using vertical bar symbol. Okay, A derive A alpha. This is one production. A derive beta. That is another. But here condition is that beta should not start with A, capital A again. Okay. So this grammar can be converted by inserting another new variable. Okay. That is A derive beta A dash. A dash is a new variable where A dash derive alpha A dash or epsilon. So if you convert this grammar by using this formula, I mean, there will be no change in the productivity power of the grammar. I mean, whatever the string previously you can generate, same thing you can generate after converting the grammar to non-left recursion, non-left recursiveness. So here you have to remember. So carefully you need to convert so that the production power of the grammar should not be destroyed, right? Or it should not be altered. Okay. So A derive A alpha or beta can be rewritten as A derive beta A dash and A dash derive alpha A dash or epsilon. Okay. By doing that, the entire grammar converted into non-left recursion, and simultaneously the production power of the grammar is preserved, and the grammar will be useful, and it can be easily accepted for either of the parts, top-down parser as well as bottom. Example of removing left recursion. See the original grammar is the previous grammar. Okay, same thing is repeated here. E derive E plus T or T. After removing by implementing this formula, if you implement this formula, okay, so here beta is nothing but here T. Okay, beta is T. So E derive T E dash. E dash is a new variable like A dash. E dash is a new variable inserted. Now E dash, and what is alpha here? Alpha is nothing but plus T. Plus T will be taken as alpha. So alpha E dash equals to alpha A dash equals to alpha A dash or epsilon. So here A dash is nothing but E dash. So E dash derive plus T E dash or epsilon. So the entire grammar, those two lines is converted into three lines. Only one extra production is added, that is epsilon, and a new variable is added, that is E dash. Okay, otherwise you cannot convert the grammar into from left recursion to non-left recursion. Okay, understood? So now, if this grammar can be easily it can be easily accepted, and it is useful for left top-down parser, bottom parser. There will be no confusion. I mean, no infinite loop can be created by the parser. Okay, is that clear? Next. Now, in as our target, now we achieve our target because we switch our discussion before. We switch our discussion to context-free grammar before we visited to top-down parser as well as bottom parser. Okay. Now, whatever the necessary things that we wanted to cover, that is already covered. We came to know what is context-free grammar, what are the core tuples of context-free grammar, and what are the production rules of a context-free grammar, what is the start symbol of a context-free grammar, and what is the derivation, okay, and what are the type of derivation, how derivation is useful to produce the string, and how the same derivation process can be graphically represented in terms of a tree known as a parse tree, and how the leaves of the parse tree collected together can be taken as the sentence. Okay, so all these things, and what is ambiguous grammar, how it is, whether it is useful or not, and what is left recursive grammar, whether it is directly useful for the parser or not. Okay, if not, then no, it is of course it is not useful. Okay, because it leads infinite loop. So how to convert or how to eliminate left recursiveness from the grammar, that also we have seen. Now these are the essential things that we cover. Now we can easily switch our topic, okay, or we can resume our previous discussion. What is top-down parser? What are the types of top-down parser? What is bottom-up parser? And what are the types of bottom-up parser? Then gradually we can know each one of them with example. Okay, very interesting. Okay, so now we can transit, okay, to our previous discussion, that is knowing in depth about top-down parser and bottom parser. Okay, so same thing is given here. Now let us switch to the topic top-down parsing. Top-down parsing. First we finish top-down parsing, okay, because top-down parsing is less. Now after top-down parsing, only bottom-up parser appear. Okay, because top-down parser gone through. I mean, some demerits has been. Demerits has been observed in top-down parser. So the next approach is bottom-up. Okay. So in that way, we can move. We let us know what is top-down parser, what are the types of top-down parser, and what are the advantages and disadvantages. Then how those disadvantages has been addressed, and the new parser called as bottom-up parser has been seen. Okay, all these things we will be knowing gradually. Okay, so now come to top-down parsing. Top-down parsing, the parser start constructing the parse tree from the start symbol and to gradually expand the production rules until the given input string is generated. So top-down parser, as per the definition or as per the name suggests, it is start from the start symbol of the grammar. I mean, it is start constructing the tree from the root of the tree. First root, then interior node, then leaf node. Okay, so in that way, it expands the entire process to the bottom, top down to the down. Okay, that means it start from the root and it reach to the leaf. Okay, in other words, the parser attempt to derive the input string from the grammar by proceedings from the root node to the leaf node. Same thing. So the main idea of top-down parsing is it start from the start symbol of the grammar. Okay, it predict the production to match the input string. Okay, it always guess or predict the whether predict the right production which can match the input string. Otherwise, it will be difficult to get the desired input string. Okay, and it expand non-terminal step by step, not enter non-terminal at a time. Only one terminal is replaced at one time. We have already seen the derivation process. Only one terminal can be replaced at a time. Okay. It continue until the input is completely matched. It continue until the input, what input string is given, that is completely matched with the production. I mean, match with the sentence generated from the grammar. If not, then there is an error. If it doesn't match after trying all the productions or the derivation process is complete, if there is no string generated, okay, now if the desired string is not generated, then there is some error associated in the statement or in the line which is written by the program. Okay, understood? Or in the, you can say, in the input symbols. Okay. So the main idea of top-down parser, it follows leftmost derivation. Okay. So remember, top-down parser always follows leftmost derivation. Okay. And whereas bottom-up parser, it follows rightmost derivation, but in reverse order. That we will discuss. Okay. Now, types of top-down parser. There are two types of top-down parsing, or you may say top-down parser. One is known as recursive descent parsing. Second one is LL1 parsing, or that is also called as top-down predictive parsing. So first parser which is designed, that was predictive recursive descent parsing. Actually, that parser was good, but it has a lot of demerits identified. That is why the second parser came to picture. Otherwise, there was no meaning of bringing another parser when the already one parser was there. Okay. So you need to think, you need to understand, recursive descent parsing is the first parser that appears or that was designed to carry out the parsing task or to carry out the or to check whether a sentence is grammatically correct or not. But that parser was a little time consuming. It has few more disadvantages. That is why second parser brought the picture. Okay. General working principle of top-down parser, it begins with the start symbol, compares the input symbol with the grammar production, select an appropriate production rule, expand the leftmost non-terminal always, and repeat until the input is accepted or any error happens. Okay. Here you take one example. The grammar is has two production. One is S derive A, capital S B, or epsilon. And what is the input string is given? Triple S followed by triple S. Okay. So here the parser need to perform the derivation or the replacement in such a way that this input string should appear. What is the input string? 3s followed by 3bs. Is that possible to get this input from the grammar given? Yes, it is possible. Why? Because there is the grammar which is given, the s derive a s b, so that s is a recursive function. It is not left recursive. It is a recursive non-terminal which can generate, which can replace itself. Okay. So start from the starting symbol, that is S derive A, capital SB. Now you need what? You need actually 3S, 3Bs. But at present you got 1A, 1B in between capital S. This capital S can also replace itself. This capital has two production. One is A, S, B, another one is epsilon. You can put epsilon here also. If you put epsilon, what you will get? Are you going to get the desired string, target string? No. Your things will close. You will get only A, B. But you will not get triple S followed by triple S. So how to do that? To get triple S followed by triple B, you need to expand S with itself. Okay. So now keeping first A constant, left side, and right side B constant, the middle S is now again replaced by its same product. Okay. That is A, S, B. So now after that, what you got? You got 2S and right side 2Bs, again in between S. Now you think. Again, which production you have to choose so that you will get 3S followed by 3Bs. Are you going to choose epsilon? Are you going to replace S with epsilon now? Is this the right time? No. If you replace, then you'll have only 2s followed by 2b's. But the string is 3s followed by 3b's. So to get that, again you need to repeat the same thing. S derive A, S, B. That middle S can further expanded as A, S, B. So now you see left hand side of S 3S and the right hand side of S 3. Now what value of S do you like to keep? Are you going to repeat the same step again? No. If you do that, you will get 4s followed by 4b's. But you need 3s followed by 3b's, which you already got. Only in between capital S is there. You have to think about. You have to disappear that S. How can you do that? What is the another value of S present? That is epsilon. Now you put the value of S as epsilon. So triple S concatenate with epsilon, concatenate with triple B. Final result will be aaabbb. Because anything concatenate with null string, the result will be the finite string. Okay. Any finite string concatenate with null string, the result will be finite string. Okay, like if you add 5 with 0, what you will get? 5. If you add 6 with 0, what you will get? 6. So any finite number will added with 0, the result will be the finite number. Same way, any finite string concatenate, okay, concatenate with epsilon, the result will be the finite string. Thus, the input string is successfully parsed using the top-down approach. Now, the parser has successfully produced the string. Is that clear? Yes. This is the general thing we discussed. Okay. Now, important characteristics. It constructs the parse tree from top to bottom. It uses leftmost derivation. This thing already told. Okay. Simple to implement, easy to understand, and cannot handle left recursive grammar as well as ambiguous grammar. Sometimes backtracking may occur in some parsing methods. Okay. This is one drawback. Backtracking. We'll see that. These are the important characteristics of top-down parsing. Now, as we told, top-down parser is of two types: recursive descent parser and predictive top-down parser, that is LL1 parser. Let us first discuss the first one, that is a recursive descent parser. A recursive descent parser is one of the most boldest form and simplest form of top-down parsing in compiler design. It consists a collection of recursive procedures where each non-terminal in the grammar is represented by a separate function or a procedure. Each non-terminal is treated as a function here. Okay, and here it consists a set of recursive procedures or functions, and here each non-terminal is represented as a function. This parser start from the start symbol, definitely, because it is top-down parser, and recursively applies. I mean repeatedly. Okay, frequently, repeatedly, and recursively. Okay, same function can replace itself. That is called as recursive. Recursively apply production rules to match the given input string. Okay, or to reach to the targeted input string. Okay. The basic idea behind this recursive descent parser is one function is written for each non-terminal. That means ultimately you can say, sir, each non-terminal is a function. But there will be no replica. If A is found 2 times in the production rule, that means it represents one function. Remember, for A, you cannot create 2 functions. Okay. So there will be no copy, no replica. I mean, A represent itself only one time. It may appear for 5,000 times in the production, no problem. But the 1,000th time it call itself. That is called as recursive. Okay. You cannot first A function 1, first second A function 2. If you do like that, the program will be run. Okay. So only A means only one function. Okay. The parser reads the input from left to right. It is the nature of every parser. It tries to construct the parse tree from top to bottom because it is the nature of top-down parser, and it follows leftmost derivation. As previously we already discussed, this leftmost derivation is adopted by your top-down parser, and rightmost derivation in reverse is adopted by bottom up. Now this is the working principle of top-down parser. Suppose the grammar S derive A is one of the production and A derive B is another production. Then there will be two functions, one representing, because two non-terminals are there, one is S, another one is A. So there will be two functions. One will represent capital S, whereas other one will represent capital, capital A means non-terminal A. The parser calls these functions recursively in what way they appear in the grammar, okay, and in what way the strings can be generated, okay. So the target of the parser is to generate the string, desired string, target string. So for that, for every non-terminal, it realize each non-terminal as in terms of a function, and it applies them recursively as per their appearance in the production rule. Okay. Example of recursive descent parser. Here S derive A, S, B or epsilon, and input string is triple A followed by triple A. This one we already just now we have seen this, okay. And what is the derivation? Here the derivation is given. First S derive A, S, B. Then as I need 3S, I replace S with its own production A, S, B. Now I got 2S in the left hand side and 2S in the right hand side. Again, I need to replace S with same value because I need 3S and 3Bs. So I did that. Finally, I substitute S with epsilon. I replaced S with epsilon, and finally I got my target or desired string, that is triple S followed by. Okay. Now this is the entire recursive. The principle of recursive descent parser. For that example, which example just now we have taken. Okay, this is the example. The grammar is given, and this is the syntax given. String given, and here is the derivation process. We have already seen it previously, and now here once again is repeated. But now the question is how this recursive descent parser works. How it produces these strings. Okay. So what it does in the first step, you see, okay, in the first step, it reads first A, and the production it applies, that is S derive. Because in the input buffer, you read A, B, 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 one character at a time. Okay, first A read, and the production it applies S derive A, S, B. Okay, now the derivation is A, S, B. Second time it read A, it applies the same function again. Okay, S derive. It called the same function because there are two functions. One is for S, one is for for every non-terminal is represented by a function. Okay, so here S is called itself. Okay, that is called as recursive. S derive A, S, B. So finally you got here 2S in the derivation or in the sentence. What you generate 2S followed by capital S and followed by 2. When third time it reads A, it applies the same thing again. Call S again. So finally, it got 3S followed by capital S followed by 3Bs. Okay. And now no S are present, rather Bs are present. Okay. So here, so before that, to see B, it apply S as epsilon, and finally got A, B, B. Now, whenever it reads the first B is matched with the first B present here. First B in the input buffer is matched with the first B here. Then it proceed. Second B in the input buffer matched with the second B here. Proceed. Third B in the input buffer, whenever it reads, it sees a B here in the sentence, which is generated by the grammar. So all B's are matched with B's. So finally, 3S matched with 3S followed by 3B's matched with 3S followed by 3B's. So input is assigned. Okay. So this is the way this recursive descent parser works. Okay. What are the components of recursive descent parser? One is input buffer, where initially the input gets stored, then pointer pointing to the input buffer, and it calls the procedure, one procedure for each non-terminal, because it is recursive procedure. Okay, it match function. There is a match function which tries to match what is there in the input buffer and what is there in the sentence, which is generated by the grammar. Okay, so if both of them are matching, A matching, then it is proceed. B matching, it proceed. If not match, suppose A is there, but in the grammar symbol capital S is there. Both of them are not matching, so S need to be expanded. Okay, so in that context, it is expanded S as A S B, again expanded A S B, and finally it replaced S with epsilon and got the suitable or the target string. These are the advantages. It is simple and easy to implement, suitable for small grammars, easy to debug, direct implementation of grammar. But the disadvantages are cannot handle left recursive grammar. It also cannot handle ambiguous grammar. Backtracking, sometimes backtracking also possible. Inefficient for complex grammar or high, big grammar. Okay, and it is sometimes need modification. These are the disadvantages. So due to these disadvantages, okay, another parser came, that is LL1 parser. Before that, before we switch to LL1 parser, it is our duty to understand what is backtrack. Okay, a recursive descent parsing with backtrack. Let us realize that. Okay. Okay, this topic we'll discuss in the upcoming classes. Okay. For the timing, let us stop it. I wish you all the best. Thank you, and have a good day. Take care. Bye. And yeah, as you are seeing these videos, I would like to request you, if it is helpful for you, please subscribe my channel and like my every video. Okay, thank you. All the best. Have a nice day.